Hello. There was a time some years ago when a boy from Florida knew better than all the math teachers from the ACT examination. That is, he gave the right answer, the boy, and all the math teachers who corrected the test had the wrong answer. It sounds unbelievable, but it was true. The problem was the following. If you get together a regular pyramid and a regular tetrahedron, the new body, how many faces does it have? Let's show first the answer that they gave the teachers, the correct answers that they gave the teachers. The teachers probably didn't do any 3D model of the situation. They thought about these cases. This is a regular octahedron and this is another regular octahedron. They have 8 faces each, and if you join them together, you get 8 plus 8 minus 2, the 2 that you lose here. So 16 minus 2 is 14. The new body will have 14 faces. Or, this is concave, it's not convex. Or if you join together 2 tetrahedrons, you get the bipyramid, which has 6 faces, 3 here and 3 here. And the formula they applied was 4 plus 4, 8 minus 2 that you lose here, you get 6. And so this is correct. And so they ask the same question, how many faces does it have when you put together a regular pyramid, that is all the sides are equal, also, that is these are equilateral triangles, and a regular tetrahedron. And they did that the same operation. They said this has 5 faces, this has 4 faces, so 5 plus 4 minus 2, 7. 7 is the right answer. But that boy from Florida, we don't know how he did it, he thought, we have a 5 plus 4, 9. But here, this is flat, so we don't add any new face here. So, and this also. So we had to subtract 1 and 2, because this is not a new one. We have to subtract these 2, and also these 2 that stick together. So this new body, it was going to have 5 plus 4 minus 2 is going to have only 5 faces, the same number of faces of the pyramid. It didn't change. We can check it here also. 1, 2, 3, 4, and the base 5. And so since that student problem was excellent, had all the answers correct, and had only this very question wrong, he went with his father to discuss the thing and to ask why they put him that question wrong. And the committee of the examination, after studying the case, they had to recognize that they were wrong. That the correct answer was the answer that the student gave, that was that this body has only 5 faces. That's pretty interesting and shows how little we study 3D geometry. And before continuing, we are going to demonstrate why this angle, the dihedral angle of the pyramid plus the dihedral angle of the tetrahedron, they add 180 degrees. Why the student was correct. And so let's think that the side of each of this body is 1. Well, let's demonstrate that this angle, this dihedral angle plus this dihedral angle, the dihedral angles of both bodies, they add to 180 degrees. So we are going to do two things. First, we are going to draw them, to estimate them. I have a Rubik cube tetrahedron, so I can measure, I can draw on a piece of paper, and it's going to be pretty accurate. Even if the bodies are on cardboard, it works pretty well. So this, I'm going to get 70, I got 71 degrees. 71 degrees. And now we are going to do the same thing with an octahedron. We are going to take also one octahedron that it's a puzzle also, a Rubik puzzle. So supposedly they are well constructed, and so I adjust the instrument, which is easily to be made homemade. It's two sticks, two pieces of wood joined together, and you can adjust it. And so I'm going to measure, this is an obtuse angle. Clearly. And this is 109 or 110. Let's say here in this case I got, this is 110, yes, I get 108. Sorry, you get 108. Well, we know that by measuring we cannot make any demonstration by measuring. But it's an estimation that approaches to the truth. That is 108 plus 71 is 179 degrees. So it could be 180. That's a flat angle. Let's now demonstrate using trigonometry. Here, if we watch this regular tetrahedron, we have a triangle. Let's say that the edge is 1. And so we have, this is 1, and this is the height of a equilateral triangle. 1, the height of an equilateral triangle, and the height of a regular triangle. That is, that triangle will be, let's put here, let's do the drawing. It's 1. The height of an equilateral triangle is square root of 3 divided by 2, and this is square root of 3 divided by 2. Let's calculate this angle alpha. By the theorem of cosine, it's 1 square equal square root of 3 divided by 2 square plus square root of 3 divided by 2 square minus 2 times square root of 3 divided by 2 times square root of 3 divided by 2 cosine of alpha. This is 1, this is 3 equal, 1 equal 3 fourths, 3 quarters minus these 2 cancel, and this I get 3 halves of cosinus alpha. So here I have 3 halves of cosine of alpha is equal to 1.5 minus 1 is 1/2. So I can cancel the 2, and cosine of alpha is 1/3. I look on the calculator what angle corresponds to that. 1 divided by 3, or 1/3, and that's 70. That means that alpha is approximately 70 degrees, 0.5. Let's leave only one digital position. 70.5. We measured 71. It was pretty good. And now we have to do the same thing with the octahedron. In the octahedron, let's see this model. This will be the angle. It's an obtuse angle. But we can see here also that it's the same angle, but we can see that one side is the height of an equilateral triangle, the other is also the height. And the third side is the diagonal of a square. So the triangle where we should calculate the angle is going to be obtuse angle triangle, where this is square root of 3 divided by 2, the height. This is square root of 3 divided by 2, and the diagonal of a square of side 1 is square root of 2. And let's call this beta. And similarly, we apply the theorem, the cosine theorem, and we square square root of 2 square. Well, let's write it. It's going to. There are many operations that have been done already here that are the same, coincidentally. Minus 2 square root of 3 divided by 2, square root of 3 divided by 2, cosine of beta. This is 2. This is 3/4, 3/4. This is 3/4, exactly the same. And here's the same operation, so it's 3/3, 3/2. Cosine of beta. So 3/2 of cosine beta is going to be 3/4, which is 3/2 minus 2. So 3/2 of cosine of beta is minus 1/2. We can cancel the 2, and cosine of beta is minus 1/3, which leads us to, with the calculator, shift calculator, shift cosine minus 1 divided by 3 is 109. Beta is 109.5. Well, we got a result it's pretty close to the one we measured. We measured 108. Well, it is a 109. Now, those values are approximately, but we can check it on the calculator because we can leave all the decimal digits on the calculator, and we can calculate. We can verify that alpha plus beta equal 70.5 plus 109.5, alpha plus beta equal 180, and so alpha and beta are supplementary. And so that makes the reason why these two bodies, this angle, are to 108, and so here we don't have two faces. We just have one face that is a rhombus, because two equilateral triangles, that's a rhombus. And so the boy was right, the teachers were wrong. But this property is very interesting, very, very interesting, and we are going to show now in the following sequence how this fact may surprise in other stuff. What we just have seen leads us to a very interesting problem and an open question also. Let's work a little bit for a while with cubes to see what happens with cubes that we all know. We have here one cube. If we have a cube of two of sides, this is of one side, of two of sides, here we will have 8 little cubes, which we can see here in wood that there are 4 cubes and another 4 cubes. So it's 2 to the third. If we have the Rubik cube, we have side C3, 3 to the third is side to the 3, the exponent 3. It's 27. So here, if we construct this with all little wood cubes, that will have 27 little cubes. If we have 4 of side, it is 4 to the third. So 4 times 4 times 4, and so this will have 64 little cubes. And also so on, 5 to the third is 125 little cubes. Well, that's pretty easy. Let's now try to construct a regular tetrahedron. Let's construct a regular tetrahedron of side 2. So at first we might think that this is similarly, if this we can construct bodies with little cubes, we can construct bigger cubes. So here, with many tetrahedrons, we can construct bigger tetrahedrons. It's logical to think that. But let's see what happens. For instance, we put one tetrahedron here, one here to have the base. How can we continue? This doesn't fit. I guess, or I bet, that we will never be able to construct this tetrahedron using only tetrahedrons. It's impossible. But let's see. Let's use another body, the regular octahedron. We take this one out of here. We put it there in the middle. And then we put the other tetrahedron, and this looks exactly as this one. So for constructing a two-sided tetrahedron, we use 4 tetrahedrons and 1 octahedron. The one in the middle looks the same because it has regular triangles, but it's a very significant different body. It's a very different body. This is a tetrahedron with only 4 faces, and this is an octahedron with 8 faces. And let's go a little further. complicate a little bit more things. That is this one, for instance. This was two-sided tetrahedron. We have a three-sided tetrahedron, Rubik tetrahedron, and we can manipulate. We will never be able to construct this regular tetrahedron using just tetrahedrons. We know this is a tetrahedron, but behind this, below this one, there is no tetrahedron. And I will tell you, and I will show you, that we will need 4 octahedrons and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 tetrahedrons and 4 octahedrons to be able to construct this. Let's do it. Let's show it. We started here. Then we have to add here to a tetrahedron an octahedron. And here a tetrahedron. And here always the bodies that are beside, one beside the other, there are alternatively an tetrahedron and an octahedron. Here I put a tetrahedron. And here I have the room for an octahedron. And here another tetrahedron. And here I have a hole inside where it fits one tetrahedron like this. And then on top of the tetrahedron, an octahedron. They are also always alternative. And now I put one tetrahedron here, and another tetrahedron here, and another here, and at last one up here. So we need, this is a three-sided tetrahedron. We need 4 octahedrons and 11 tetrahedrons. Unexpected, inexpectable. Who expected this? And it's very interesting. And always the colors are alternative. I mean, there are different colors to show that exactly that this is a tetrahedron, octahedron, tetrahedron, and I have this the same here: tetrahedron, octahedron, tetrahedron, octahedron, tetrahedron. They are alternate. And that phenomenon probably will pass the same. Will be the same here. I have a tetrahedron here. I have an octahedron here. A tetrahedron, an octahedron, like that. I'm going to challenge you now. But here, we built already this one. The challenge is, if I have a 4-sided regular tetrahedron, how many tetrahedrons and how many octahedrons, how many of this and how many of this, we need to be able to construct this body. You have to find out, to investigate. No? This is for sure, is that you need tetrahedrons and octahedrons. That's sure. But the question is, how many of these ones and how many of these you need to be able to construct a 4-sided regular octahedron? If you find the answer, send me, and I will give you comments and tell you whether you are in the right way, if your answer is correct. I would like to see you working and to see you finding the answer. That would be delightful for me. Thank you very much.